All right, yeah, well, thanks for coming. My name is Matt. Urbit ID is mastyr-bottec. Someday it'll be mastyr-bottec once we have enough. We actually have to pronounce them correctly. But, so yeah, this is like UIP-0103. Raise your hand if you heard about UIPs. I like to call them whips. Okay, yeah. So like this is the new way to improve Urbit's core technology now. So actually Native Planet already added the lick vein, which you heard about from Reed a little bit. So Mopful I think he's still putting together the whip for that one. But anyway, so this is the project I'm currently working on right now. I'm fairly excited about it. I was going to give a talk on like how to be a dummy and work on core technology at Urbit, but it's like I kept trying to hack it out. It just didn't fit. So I'm more interested in what I'm working on currently anyways. And I'm excited about this because I've learned a ton about Urbit along the way that had always just thought of sort of the black box part of Urbit. So yeah, so most of you heard about UIPs, but raise your hand if you've used sigless, this caching rune. Do we have a laser on here, by the way?
Yeah, the top button. It's so light though.
It doesn't really show. Swing it this way.
Oh, I see. It doesn't show up on the screen.
Oh, sorry.
Right in your eye.
Yeah.
So I missed the hands. Who's used sigless? Okay, less so. Okay, yeah. So sigless is a sig rune, so it's a hint rune. But we'll get into what it is and see here. Yeah. So pretty standard outline today. Give you a little bit of background on what sigless is as it currently exists. The motivation behind why we want to change it, upgrade it. Delve into the design and implementation of the thing, and then wrap it all up and tell you what I just told you. So, first thing is, pretty much I do have to give acknowledgments first off to Rob Nisserkfer, to Ted, because he's like I think he's the #1 spec machine in the Urbit, which is appropriate given being the CTO of Urbit Foundation, but yeah, so I just tried to pick this thing up. Like Joe has been wanting this technology that we're talking about for a long time, and then Paul Fidwhite Ragful, he helped me a lot with the implementation on the C side. But so those are the acknowledgments there, and let's go to the background. So sigless is it's a very simple rune. It just takes some hoon. Okay, so P is like your hoon expression, technically called a hoon, I think still. So we're gonna take that and become this. Sigless of tomorrow. Okay. All right, well, what is sigless? I think this is actually the example from the docs. It's nothing too complicated. It's not the Ackermann function. It's a recursive Fibonacci gate to produce, the Fibonacci of A. So here at the top, we're providing the input 35 to our gate, which is A. And then we're branching on whether that is less than, we check our base case, right? I mean, everyone remembers Fibonacci, but if you try to do it on an interview, you might get hung up. I mean, I didn't. Maybe. And so it branches, right? And if A's, I don't have to walk through it completely. I think you get the gist, but it's going to nest a lot of core, and it's going to unfold a lot of buck calls, which are the recurs here. So without any sigless here, just the humble calculation of Fibonacci for 35 is like 16 seconds on my Apple Silicon chip. So pretty slow, not really too acceptable for what should be a mature technology. But you add a sig less to the top there, right before the what call, and you get 142,000 times boost in speed. Okay, so I didn't do that. That wasn't. I mean, I'll take credit if you want to give it to me, but no, I didn't do that. So this is good. So you're probably already starting to think. You can kind of maybe foreshadow what this thing does, but sig less is the cache of computation rune. Let's see. I think we.
Pointing towards the laptop over here.
Okay, right. No, we're good. Okay. Yeah, so I do want to explain this a little more though. Like, what exactly is it caching here is not really clear off the bat, right? It's like, how do you cache that whole what call, expression? It doesn't seem immediately obvious. So I guess the Hoon compiler is taking this and essentially rolling it out. So you're going to get not just one sig less call, you're going to get lots of them, for each value of A. So you're getting like Fibonacci of 1 and 2 and 3 and 5 and stuff, or even maybe if there's a 4 in there. You're getting all of those inserted into a memoization cache, which is in memory. And so when you're going through it, when it's all like boiling back up in the recursion, you already have those values in the fast memory cache. And so it doesn't have to recompute anything, so it's extremely fast. Oops, okay. It actually works towards the DV too. And that's kind of like I guess I just pulled that one from the Google, but that's pretty much what we're talking about. All right. All right, so what does the Nock look like when we use zap-tiz to compile sig less? So it's a hint rune. So everything all the hint runes expand to a Nock 11. And then after that, you just got like the term, the send memo, that is the hint type. And then after that's called the clue, which can be, here we're just producing, the constant 0. And then it's the formula you actually want to cache or retrieve. So we'll talk more about the clue later. But this is a dynamic hint. And that's because technically you can put a different clue in than the 1-0 formula. It'll become important later on. Hopefully I don't bore you to death. Yeah, this is fair warning. I should have given the fair warning earlier. We're going to get into some fairly, I'll keep it high level as, but. So sig less, it caches a subject formula as a key, and the value, the product, is the value in a essentially a hash map on the runtime side. Here's the caveat. And this is from the docs, right? And this is not like a bad thing. It's just the current state of sig less is these computations are only, they're transient to the current event. So if you wanted to hold on to, expensive computation, and use it in a subsequent event, you can't do that right now. And so that brings us into the motivation of the upgrade. So transients is I guess the biggest reason why the SIG-less needs to be improved. There's some user space things like, has anyone seen Landscape's mark warming thing? Yeah. So I think Peary and somebody else, maybe Jose, stumbled upon this a little while ago. Submitted an issue to make Landscape a lot faster, because essentially the marks converting between some of the Hoon data types and JSON were not being cached. And so they were just really slow. It's like every time you wanted to do any sort of interaction in Landscape, it had to recompute. So yeah, the mark warmer was the way to work around that with the, did they use SIG-less for that? I'm not sure. No, but they had mark warmer anyways. But I think the kernel space is the main motivation for this, because without the persistent caching, you incur a good amount of complexity and I guess I'll say lethargy. It's not a technical term, but not the best performance, right? So like the three categories I have here: Ames message deduplication, forward caching, and Arvo vein activation type checking. So I'll dive into one of those. So like, this is the opportunity though, right? Like there's a limitation with SIG-less as it currently is implemented, but adding sort of a persistence to SIG-less means we kind of get a thunk. Who's familiar with thunks? Okay, so yeah, I'm not super familiar myself, but as far as I've understood, thunks are common functional program, like other functional programming languages have these things called thunks, and what they are functions that take 0 arguments. And then you essentially wrap an expensive computation in a thunk and give it a symbol. And then the compiler sees that it's a thunk and can lazily evaluate it. So typically, I think in Haskell it means that it's only ever evaluated when it's needed. So you can pass it around without any extra computation costs to functions that want to use that computation. You see, with our SIG-less being persistent, they're not going to be lazy. The types of lazy thunks that don't clean their room or make their bed. We're going to have some industrious thunks. This may be, so because we're strictly evaluated in Hoon means that computation is going to be immediately evaluated, right? So not lazily, but we still hold on to it and can use it again and again when we want. So yeah, shoot. Laziness isn't generally good, and I think there's a broader discussion there. Technically and otherwise, I don't think there's no discussion otherwise, but yeah. Could go more into that if I have time at the end, because there was an interesting critique around this, being able to implement thunks in Hoon or not. But yeah, if you're interested in that discussion, definitely talk to me afterwards. So that's persistence. With the path parameter, remember the SIG-less P is a SIG-less and then a path P. This enables us to actually target a special cache if we want to. So if you want to use, I don't know, if Ames wants a cat, or you want to prioritize certain computations over other ones, this opens the opportunity for that. Specialized caching, custom tuning. I asked that question, which other systems have this type of specialized caching, because I think it's kind of interesting. Obviously, caching exists in a lot of them, but being able to target caches, well, in functional language, I don't think they have that. I've never heard of it. Has anyone heard of specialized or like custom-tuned caches?
Python.
Okay, Python has that?
Yeah, you do an annotation in LRU cache. I think that might.
Okay, that's cool.
Tune each one. Yeah.
But Python's not functional,
It's
so
not functional and it's not persistent. So.
yeah. I mean, you mentioned databases, like SQL databases, or maybe even NoSQL databases can like have custom-tuned queries, and they can even like, you know, pick up on query patterns that repeat often and, you know, tune themselves based on that. But I think it is fairly neat, something interesting or maybe novel in urbit. Yeah, so these typically complex systems can become stateless. The example I'll go into a little bit, which is actually included in the WIP, is for Ford. Ford is I guess it's technically not its own vein anymore, right? It's in clay now. Used to be its own vein. And I looked back at the blog posts on urbit.org just to see, what's the history of the development of this thing been. In 2018, it was labyrinthine and poorly factored. I don't know who wrote that. That sounds like an insult, fighting words right there. But so in 2020, one of the well-known engineers proposed moving it into clay, and then so that simplified it, and that's kind of what we have today. But 2023, I'm hoping that it can be so simple it's trivial, and if it does become that way, anyways, is anyone familiar with the naming schema of the Ford so far? Like I guess the skunkworks names for Fords. So like Ford started off as just Ford, and then it became well, there was an attempt that never got shipped called Ford Turbo. Okay, Ford Turbo. That didn't make it out, right?
It did.
Oh, it did. Okay. Oh, that's the labyrinth. Okay. Well, turbos do, right? On turbos, labyrinthing.
Yeah, I mean, it was actually a shortening of Ford Turbo Encabulator.
Oh, not a turbocharger. Okay. And then Ford Fusion?
Yeah. And Fiesta was the one in between.
But yeah, there was a Fiesta? Okay, Fiesta? Fusion?
Yeah, there's also Ford Pinto in early 20s.
No, Ford Pinto. So, let's go Ford Lightning. That's what I want. Rest in peace, Paul Walker. All right, so yeah, design. This is like how it's proposed to work now. This is kind of, so a path is just a list of terms, I think. And so in this new design, if you just have the empty path, the FAS, it just goes into the transient cache, which is the same cache that we have today. With like a known path, like forward or aims or something that we implement later down the road to be known, that is it's targeting a persistent cache that's also specialized. And then anything else just goes in a persistent cache. All right, so this is the fun part. I was talking to Ted, and he's like, calm down. No one is born with an understanding of Ver's bytecode interpreter. So this is the black box part. At least it was for me. So yeah, has anyone taken a look at Nock.c in Ver? Okay, nice. Yeah, neither had I. I mean, I did glance at it, and it, this is the thing that actually makes Nock run. So it's a very important part of the system. I guess, yeah, that's the lowest level of the system. That's like the heart of Ver. It's the connection between Unix and, Earth and Mars. And it's what's called a stack-based bytecode interpreter. So, yeah, I'll just try and get you up to speed with what I understand about it so far. And yeah, this is the most exciting part, right? Because I figured I would never touch the bytecode interpreter. Nobody touches the bytecode interpreter, So here's what it does. Yeah, it compiles a list of ops. So these aren't the op codes in Nock, the 11 or 12, but it's like a list of 95 op codes that are used to tell for later execution. Okay, so those are the ops. I imagine I didn't look at the tokenization part and the parsing part of the Nock, but yeah, chugs through the Nock that it gets and compiles a list of op codes. While it's doing that, whenever it sees a Nock 11, which is the hint, Nock, it parses those in a special way, or I guess, yeah, special way, and it emits hint-specific ops to the list for those. And obviously we're working with send memo here, so that's kind of the area where we were working with. And then the next thing, it takes that list of ops and assembles what's called a bytecode program. And this is all happening on the loom. So it's pushing and popping things on and off of the loom stack. Which, for those not familiar, the loom is the memory arena that Ver maps. The assembly part calculates the literals, the call and registration sites, the memo slots, and the actual bytes. And then finally, the burn step is executing the bytecode program. So skips through the bytecode. Actually, skips through is kind of an important point, because certain ops that are emitted to this list, you don't actually want to evaluate, for example, an if-else, depending on the truthiness of the condition. Then you might want the if, you might want the else, right? So we have to know that ahead of time and be able to skip over one of them. Yeah, and then when it's executing, it jumps to those ops that have computed go-tos. And so I've heard, I don't quite understand this part, but apparently the computed go-to pattern is a very common old school way of writing code, with, I don't know, forth, I think I've heard, is the example that I've heard. but it's the main reason why the bytecode interpreter is somewhat fast. And we didn't always have a bytecode interpreter, actually. Before that, we had like a naive tree-based interpreter. And so, yeah. So in order to enable the functionality of the new SIG-LUS with the persistence and the specialization, I had to work on various parts of this Nock.c. So like the way it works is, right, this is like a runtime feature. I mean, it's like something that Hoon requires, well, it doesn't require, right? It doesn't technically, because hints, right? Hints just say, hey, maybe you want to do something special with this. So the runtime, yeah, I already talked about the subject, like the subject's on top and then it does some computation and leaves a product. And then there's some like opcodes, which are fairly, well, they're actually, the names look worse on first glance than they are. Like the B, the suffix, the B, skib versus skis, slib versus sleaze, slies, I don't know. Maybe I don't know. They're, those are the opcodes that are responsible for actually looking up a key in our cache. And then the save one is for, obviously saving. So yeah, let's see if we could walk through. Like, think of the stack that we've got. It's technically not like a stack that just goes up and down because the way the loom is and the road model, it's like we're growing in and out, north and south roads. And the extra part of the persistent SIG-LUS is that when we get a cache miss, so a computation that hasn't been cached yet, we need to actually like insert some extra information into that stack frame that tells us that we want to save this thing to the persistent cache if we have something other than an empty path like you saw in the design, right? And so just adding that little bit, just that one bit, like you have to make sure that all the other parts of the interpreter that interact with the stack know that that thing is there, because this sort of stack context is crucially important for all these functions to work, because otherwise you might be looking at a piece of data that you expect to be this, but it's actually not. It's actually got this save bit on the front of it, and then it crashes everything, right? And then later, right, we use that bookkeeping information to see, okay, we're doing a cache save now, so is it going to be a persistent or a transient or a specialized cache? And then we can use that to do the correct like hash map save. Okay, cool. Yeah, so that's all the pain I'll inflict on you today. Let's see. Yeah, so like that's the gist of it, right? I'm like almost done with the var side of this. So the runtime implements what we want for the most part, and what I have, I've tested it on all the veins so that I can use it, but I haven't actually upgraded the syntax for SIG-LUS, and in fact, it might actually become like a SIG-HEP or some other rune just for simplicity's sake, and we'll see about that. It may be a new rune, but it'll certainly be a Kelvin decrement for Hoon. And yeah, it was going to have persistent specialized caching. There's some like waterfall performance gains we can get from this feature. I'm not sure how how significant those will be, but I think fairly. Yeah, and then I omitted some discussion over Nock 12, which is the only virtual Nock opcode that we have, which is used for Scry. But yeah, I'm happy to go into any sort of deeper on any of these things, but hopefully that was interesting and a little bit more of a window into what I guess I'll have to stop calling the black box. So yeah, thank you.
Do you have any questions?
So if you don't make this a new rune, isn't it a breaking change? Wouldn't you have to specifically specify a empty path if you're just...
Yeah, exactly. So yeah, there were roughly 100 SIGLess calls, and it's just a find and replace out of the gates. And you think like, would we want SIGLess to be like variadic, to take like a variable number of children? Probably not. But yeah, you're right. If we do upgrade SIGLess, we've got to find and replace.
If we upgrade.
Yeah.
But also,
There's a way to do this in a backward compatible manner. Basically, it's we can go into the details, but yeah. So the SIGLess rune itself, yeah, we'll have to determine whether that takes zero, whether it takes just one parameter or whether we have it always take two parameters, and having it be variadic probably doesn't work. So we could add a second rune, as Matt mentioned. Or we could just leave SIGLess as it is, don't touch it, and then if you want to use persistent caching, then you drop down to the lower level SIGGAR raw hint syntax, which is what you saw in the example for Ford there. And in that case, we don't have to change Hoon at all.
Can I put that back up? Now it'll be taken down for copyright violation. Where's that? Oh yeah, I guess I didn't include a SIGGAR. Yeah, that's too. Did I?
Oh, full snap.
It's in your trivial 4.
Yeah.
Oh. Okay, yeah, cool. Yeah, right there. Little. So that's how you can hint sort of directly. And all the other hint, what are the other runes that boil down to the SIGGAR?
Any SIG rune.
Any, yeah. Yeah, so all the hint runes boil down to SIGGAR.
So one more question. As someone who's tried to figure out what the benefit of SIGLess is the primary use case in recursion, as your example was?
No, I don't think so. Just any expensive computation you want to hold on to and use again. Yeah.
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 Anybody else?
First of all, this is sick. Second, yeah, I was wondering if you could talk about how this will impact everyday users and developers for builds.
For builds, well, it depends on somebody using it for Ford to make a faster Ford. So you want to do that?
I think it would be cool if someone
That'd be
did
cool,
that.
right? You have to call it Ford Lightning, though.
Yes.
You mentioned that there's 3 kinds of paths you can use to annotate these SIGLesses.
Yeah,
You have the transient ones as we have right now. Then you have dedicated, persistent specialized,
Yeah.
and anything else. Is there a world here where the anything else also contains some information that lets you specify about, oh, I expect this to get hit very frequently for a short amount of time, or occasionally over a couple of days, something like that?
That seems like perhaps a future feature, right? Yeah.
Yeah, I actually think that that's a good
That's
reason
cool.
not to make a hoon rune for it just yet, right? Let the hint change shape, and then once we kind of have used this a few times and know, what it's going to look like, maybe we do want to add more metadata, then make it a rune.
Nice.
Yeah, I think somewhat along those lines. Are all of these caches going to live in the loom? Or are there any plans to kind of like have something else, perhaps?
Yeah, so this is in the loom. Yeah.
I don't quite maybe I missed it, but what's the difference? But what do you mean by persistent, specialized, and persistent? I mean, I look at
Just
persistent if it, yeah.
Yeah, so persistent means that the computation will be cached across events. So yeah, until our cache reclamation policy evicts it.
Is the cache reclamation policy related to the path that you give it, or not?
No,
Okay.
I guess it could be. It could be someday. Yeah, it could be. Like, you can imagine, like all these the specialized features of this, like having a specialized backend cache. This is just like the opportunity that's open now with this work. So somebody wants to work on the Ford, and they say, all right, we're going to use this, and not only we're going to use persistent caching, but we also want a Ford-specific cache that has some special logic for tuning or reclamation. So those would just be PRs,
Okay, yeah, I see. I guess I misread the middle part as like one long path, but you're saying there's one, there's two, and there's many others. Those are the specialized ones.
Yeah.
Anything else? Okay, that makes sense.
And we haven't defined any of the specialized ones yet, right?
Right.
But they could be AIMS, Arvo, et cetera.
Cool.
Yeah, just to give a little example of why you might want specialized caching and not just throw everything into the same big cache. So you want Ford caches to behave differently from AIMS packetization caches, for example. So Ford build cache, you're caching the compiler and the parser, the Hoon compiler, Hoon parser. Each time you run that, it takes a long time. You want those caches to stick around for a very long time because you actually only do a Ford build every once in a while. And so you actually, you want it to persist for a long time if you can. AIMS packet caches, what those are for is for, well, there are a couple different ones, but we can talk about the AIMS serialization cache, which is what could replace there's a manual deduplication logic in AIMS right now that does at least linear traversal of every outstanding message that you're trying to send, so it's pretty slow. But we need to do that to make sure that the memory doesn't get duplicated, so it doesn't use too much memory. And so so for that cache, you don't necessarily need that to hang around for that long. But you might have a lot of them, a lot of cache entries, right? So you might want to say, like, yeah, this cache can get really big, but actually don't hold on to them for that long. Each entry tends not to be as large as a Ford cache entry. And then we may also add another cache for AIMS that's for caching packetization, so taking one slice of that packet and encrypting it, sticking a packet header on it. And in that case, you want that to be a very short-lived cache. You don't need very many of them because it's mostly just going to get used a couple times. And so, right, so each one of these you want to have like few different kind of knobs that you can turn to tune to optimize each cache.
So this question will pull us a little bit out of the depth of the caching, but this is UIP-0103. Do you have any kind of reflections on the UIP process so far, or how's that experience been?
It's pretty good. So there are a number of UIPs that definitely recommend checking them out. Like for Joe's talk yesterday, there are 2 whips with that. Yeah, I think it's good. I mean, it's not overly formalized. It's not like an RFC. someday you won't be able to go talk without having a corresponding whip. Maybe. But I think I guess the highest friction part has been like writing a whip after the fact. Like after it's all done, it's like somebody has to go back and actually make sure that the document reflects, the implementation, and that's kind of a pain. I think that's happened in a number of cases. Like lick is now being written as a whip after well, it's just about merged, and then yeah, at least a few times now. So yeah, it's not perfect, but I think it's good because it's like, this is open. It's at urbit/UIPs with an S. So, anybody can visit, take a look, submit a PR to improve a whip that exists already or submit a new one. And, there's like a process that goes through. This is probably a different talk, but yeah, it's good. It's good. Works.
Any other questions? No other questions? Okay, let's give it up for Matt, everybody.